Good afternoon. I'm happy to introduce to you Professor Kazuhisa Makino from Reims Research Institute for Mathematical Sciences. It's a very highly estimated research institute in mathematics. It's a part of Kyoto University, and Professor Makino is leader of computer science group there. And Professor Makino graduated from Tokyo University and worked for a long time there, but then he moved to Kyoto and is working there. And he's showing the slide of a person who was co-author of Professor Makino and my professor, Leonid Eugenovich Khachiyan, or in English just Leonid Khachiyan. He was famous. In Russia we don't have many famous computer scientists, but he was one of them, definitely. And he has a very famous result for proving that the problem of linear programming is polynomially solvable. But he has many other very nice results, and one of them is sub-exponential results on dualization problem. And this is the problem which will be discussed by Professor Makino. So we dedicate this presentation to the memory of Khachiyan, the co-author of Professor Makino and my teacher.
Thank you. Leo is a nice friend, but unfortunately he died. Okay. Thanks a lot for Professor Sergei Kuznetsov for inviting me this great opportunity to have a talk here. Okay, today I want to talk about the dualization of the monotone Boolean function. Right. Of course, many results are joint work with Leo Khachiyan, right? But what is the problem? Problem is easy, just one-page definition. I think that everybody can understand. If you do not understand, maybe my mistake. Okay, so what's the problem? Okay. So you know the Boolean function. We have a Boolean function, f, which is a mapping from n-dimensional 0,1 vector to 0,1. So n is a finite, n is a positive integer, right? So we restrict the Boolean function monotone. So what is a monotone? For any two vector, b and w, if this inequality holds, then the function value f of b is at most f of w. This is a monotone. So here, inequality is a bitwise. I mean the ith bit of b. So b sub I is at most w sub I. So bitwise inequalities. Look at this example. So here is a three-dimensional hypercube. So we have a 2 to the 3, so 8 vector from 0, 0, 0, 1, 1, 1, right? And the monotone function looks like this. So this is true, the area such that the function is 1. Because if some point is 1, for example, 1, 1, 0, if this is 1, then according to, so this value is 1, right? According to this implication, 1, 1, 1 must be 1. So it's close above, right? It's a simple function. Okay, Boolean function can be represented in many ways, but the two famous and important representations are CNF and DNF. The first one is a conjunctive normal form, CNF, which is a product of sums. So we have two sums. So of course, it is a logically sum. So disjunction, and here is a conjunction, and here. So this means the phi is true if x1 or x2 is true, and x2 or x3 is true, and x3 or x1 is true. This is a function. And here we restrict a monotone function. It means no negated variable, xi bar, appear in the formula. The function is monotone if and only if it can be represented by the formula without negative literal, right? And dually, the Boolean function represented by disjunctive normal form D and F, which is a sum of the product. So here we have 4 terms, 4 monomials. So if psi is true, if one of them, at least one of them is true, then true. So in this case, if both x1 and x2 are true, or both x2 and x3 are true, or and so on, right? So again, we restrict the monotone. We have a formula without negative variable, negative literal. Okay. The last definition is here, primeness. So look at the last term. You can see this is a redundant. Why? Because if this is, so this is or, right? Or. So if the last term is true, it means that x1 and x2 and x3 all are true. Then, for example, x1 and x2 true. This term is true, right? So we can remove it. This is called prime DNF. Similarly, we can define prime CNF. So in other words, if you regard this is a hypergraph, the family of set. This is a family such that this is a set whose members are 1, 2. This is a set whose members are 2, 3, 3, 1, 1, 2, 3. Then this is a superset. For example, this 1, 2. So then we can remove it. So we take only the inclusion minimal set. Okay. We can get the prime DNF. So this implies we have a unique prime representation, unique prime DNF and unique prime CNF if the function is monotone. Okay, that's it. Now we can define the problem. The problem is simple. We have a CNF, which is a some monotone function, monotone Boolean function. Essentially, we can restrict it, give a monotone, prime monotone CNF. How do you compute a prime DNF, which is equivalent to the phi of f, right? We have f. Right? Very simple problem. So look at this example. Phi is this one. How do you compute this? The simple version, simplest way is just an expanding formula, right? So x1 and x2 and x3, we have this term, x1, x2. The second one is x1, x2, x4, right? So we do this, right? Then now we are interested in only the minimal prime term, right? Minimal term. Then we remove it. Then we get the prime DNF, right? Of course, this procedure is not efficient at all because, right, last final prime DNF is quite small, but the intermediate size, this DNF is quite large. The problem is how do you compute from CNF to this one efficiently? Okay. Everybody understand? Okay. I want to say there are many, many applications to the AI database theory and so on, especially for the formal concept analysis, which Sergey do this. Yeah, Professor, yeah, Sergey do this. And many, many polynomial or quasi-polynomial equivalent to the problems, are many, many. Here I explain 2 examples, which is simple, but looks quite different. So one is quarterly in the database distributed computing. Okay. Okay, let's consider a very simple case. We have one database. To manage, to control this, we have a server, right? So if you want to access to the database, we have to ask to the server. So here, some user or some guy want to modify the database, then we request to the server. So here, both is a kind of the permission. Once you get the permission, then you can access this. right? Then after modifying the database, we return to the permission. And some other guy want to modify the database, then we get the permission balls, then we access to the data. And at the same time, some other guy want to modify the database, but here, no ball, no permission. So he cannot permit it to enter the critical section, right? A very simple way to controlling a database, right? All right. So one of the problems is this is a fault tolerance problem. If the database is alive, it's safe, but if the server is dead, then we cannot access to the database, right? So to overcome this, we create several servers, right? So each server has a ball permissions. So if you, how do I say, consider the following way, then it is, okay, if we want to modify the database, then we have to get all the ball from the servers, then similar problem, right? Similar fault tolerance problem appears, right? So in this sense, we, how do I say, create many groups, many set. So in this case, we create this set and this set, 3 groups, such that there is a common point, common server in the different groups, right? So in this case, this group and this group has a common server here. Then, so if we want to modify the database, we choose one of the group. For example, if we choose this group, then we get all the permission from this group, right? If you collect balls from this group, then we can access this. At the same time, some other guy want to modify access to the database, then he also choose some group. For example, if he choose this red group, then he also want to collect all the balls, but this server has no ball, right? Because his ball is here. So because of this intersecting property, right? So he cannot permit it. He is not permitted, right? Okay. So this is called the quotary system. So more precisely, what is a quotary in the distributed system? So we have so B is a set of servers, right? So in this case, 1, 2, 3, 3 is a set of servers. We have groups, Q1 to Qm. In this case, Q1, Q2, Q3. And the hypergraph family of a set called quotary if 2 conditions are satisfied. The first one is I already mentioned, the intersecting property. 2 set has a common point, right? That's why we cannot access to the two guys never access simultaneously. And the second one is a minimality condition. If the Qi and Qj is different, then Qi is not a subset of other guys, right? If you want to consider the access, right? The bigger set is not necessary, right? So which is not efficient. So we consider only minimal set. Okay, this is a quotary. The one more definition. A quotary is called non-dominated, good one. If there is no set Q which satisfies this condition, C union Q minus this one is not quotary. Okay, if you don't look at this, right? C union Q, right? We want to enter the critical section. It means that if you have a more group is better, right? So it means that we can enlarge. So this part is essentially we remove the larger Qi which contain Q, right? Which is not necessary for the access. right? So it means non-dominated is there is no such Q. So it is efficient in some sense. Right. And this problem is equivalent to the monotone dualization problem, which I mentioned. I mean, the deciding we have a quarterly, checking this is non-dominated, is polynomially equivalent to the monotone dualization. Okay. Some questions? Yeah.
And what if a server in the intersection fails?
Intersection fails. But this is not the problem, right? Intersection, if this guy fails, right? Then, so these two groups, we cannot use these two groups, right? Because he cannot pass to the ball, right? If this is died, right? So in this case, we have another family, another group right here, right? They can access these groups, right? It's clear? Mm-hmm. Okay. Okay. So this is one example. The other one is related to the functional dependency in the relational database. So again, I use a simple example. So we have a table, 6 rows, and the column represents teacher, which teacher teach some class, right? This is hour and this is room. For example, the first row says Professor Arman teaches in the morning, Monday morning, at room 120, right? The second row says Professor Fagin teaches Monday morning at room 111. 110, right? If you look at this table, you can see something strange. For example, if you look at the first and 2, 3, 4, fifth rows, right? This is strange because same teacher and same hour, but he used a different room. Strange, right? Of course, you can say the room 120 and 100 is a connected room, and you cannot say this, right? So in this sense, we have a knowledge, right? If the teacher and hour, T and H is determined, then R is determined. So R is this way. So in this case, we have we can find some contradiction. So this is called functional dependency. So the other one is this one. So a different teacher, Fagin and Meyer, teach Wednesday afternoon, the same room. Right? Again, we can see if the hour and room are decided, then the teacher should be decided. Right? So in this sense, if you construct a database, for example, relational database, so many dependencies are used to control the table, relation. The functional dependency is one of the famous and important dependencies. And maybe 2 problems. So let's consider the following problem, right? We want to construct a functional dependency, right? We design the database. So problem is of this. So one is we have a set of the functional dependency F. How do you compute the relation that satisfies F only? So this is called Armstrong relation. The other one is that we have a relation. How do you compute a set of the functional dependency that's holding R? So if you are, this example, if you have a table, right, then we can find a functional dependency, right? Once you compute a functional dependency, we generate a relation. Then again, look at some inconsistency. Then we modify the relation. So it's the opposite we can do this. So the designer used these algorithms. And interestingly, if the, of course, if the relation satisfies some normal form, then yeah, these two problems are polynomially equivalent to the monotone dualization, which I mentioned, right? So this is looks different problem, but the same problem for the monotone dualization problem. Okay. Okay, now come back to the monotone dualization. So you remember, right? We have a CNF, how to compute a DNF, prime DNF. So you can see some Japanese word to learn. So this is an example. Okay, so what is the complexity? So different from the traditional one, I want to say the output size might be large, quite large, exponentially larger than the input size. For example, consider following CNF, conjunctive normal form. We have a 2k variable, x1, x2 to xk, and y1, y2, yk. And consider these quadratic clauses. Okay, for example, if you consider the case in which k is 3, then we have this CNF. Applying just an expanding formula, right? We get 2 to the 3, 8 terms, right? All are minimal, because here any variable appears exactly once. So it means the expanded term is all are minimal. 2 to the 3, 8. So in general, we have a k clauses here, then we have a, right, yeah, 2 to the k terms. So I want to say the input size is linear in k, but the output size is exponential in k, right? So we regard the monotone dualization as a generation problems. I want to say we generate the term one by one, right? So what's the complexity class of the generation problems? Okay, here's the time axis. So algorithms start this point. Then this is a generation problem. So the algorithm output the first item, alpha 1 here, and second item here, and maybe p minus first item here, and pth item here, and output the last item, and stop, halt. Okay. Okay, let's t total denote the total time. This is a time interval between start and halt. So TP denote the time interval between, yeah, these output. The first one is called output polynomial time. I mean the T total. Total time is bounded by the input, polynomial in the input and output size. So this is the first concept. The second one is called incremental polynomial time. So this TP, time interval, is bounded by polynomial in the input size and output so far, right? So to output the piece item, right? This interval is bounded by the output item. I mean, outputted so far, output so far. The last one is more easy. So each time interval is bounded by polynomial in the input size, right? So of course, you can see this is a better concept. This is a worse concept, right? Because this is each time interval is bounded, but this one is time interval is gradually increasing because of this last term. This one, the last one is doesn't, yeah, take care of the time interval. The worst case, we just bound the total time, right? Maybe the first item appear here, and second something here. Right? So this is a better concept, this is a worse concept, but still okay. 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 So okay, if you don't like a generation problem, let's consider decision version. Maybe this is also instance. We have a monotone CNF and monotone DNF. How do we check? These are equivalent. Just a decision problem. And Korbiev and Professor Ibaraki shows the following three statements are equivalent. So decision problem is solvable in polynomial time if and only if generation problem, computation problem is solvable in output polynomial time. And also this is equivalent to the incremental polynomial time. So these are non-result. So if you don't like a generation problem, just consider the decision problem. So in other words, we have a two representation. One is a dual representation, right? How do you check these are equivalent? Okay. And polynomiality, it is still open. Many big guys mentioned this is open, including Khachiyan. Khachiyan is where here. Khachiyan, yeah. Several big guys are here. Yeah. And I didn't update that. This is a list of until 2002. After that, of course, Professor Kuznets also mentioned this. Yeah.
We have Babin.
But sorry, I didn't update. Yeah. And many survey talks or paper mention monotone dualization is important. The first one is Japanese, you cannot read, but Professor Toshi Ibaraki. The second one is Johnson, right? You know the Gary and Johnson book, Johnson. He mentioned this is an open problem in NP completeness in 1991. And Robash mentioned this problem as a combinatorial optimization. And you know the Papadimitriou, he also gave an invited talk in the iCarp in 1997. Is an open problem of the NP completeness. And Manila mentioned this as a data mining problem, 2002. And Thomas Ide and Gottlob mentioned this is a problem in logics and AI, 2002. So I didn't modify after 2002, sorry. So this is until 2002. So what is best known? Your best known result is due to Fredman and Khachiyan in 1996. This can be solved in quasi-polynomial time. So what is N? N denotes a number of, okay, if you restrict a decision problem, we have a monotone CNF and monotone DNF. The indicates this is the input size. N denotes the input size. And the problem monotone duality test can be solved in n to the log n over log n time. Right? This is not polynomial, but the quasi-polynomial. N to the polylog n time. Of course, there are several other quasi-polynomial results are known, but they're essentially same as Fredman and Khachiyan. Okay. So I mentioned this relationship, duality testing, decision problem, and dualization problem. So Khachiyan's result also implies this one. So he shows a quasi-polynomiality here. It automatically implies incremental quasi-polynomial time and output quasi-polynomial time, right? So this is the result. Okay. Now I want to discuss the problem looks not NP complete, I want to say. Okay, now consider non-monotone duality. Just negate a duality problem, I mean testing problem, decision problem, to make it belong to NP. So the same problem, we have a monotone CNF phi and monotone DNF psi. We want to check these are not equivalent. Then you can see this is clearly belong to NP because if we have a vector assignment B such that phi of B is not equal to the psi of B, this is evidence. These are not equivalent, right? So this evidence is a polynomial size. It automatically implies this is belong to NP, right? So non-monotone duality belongs to NP. And most of the theorists believe that NP is not a subset of the NP is not solvable in quasi-polynomial time. Of course, this is not shown, but it's believed. And it implies that monotone dualization, monotone duality, non-monotone duality is not NP complete. Right? Another evidence is called the guess bit, a non-deterministic bit. So Thomas Ait and George Gottlieb and I show the monotone duality problem can be solved in the log square bit, non-deterministic bit. And again, so this shows this is so-called beta 2p, but we forget this. But how do I say? Most of people believe that beta 2 problem is not NP complete. So it means the monotone duality is not NP complete. Okay. But of course we don't prove. But if we prove this is not, not polynomials, it is quite difficult because we don't know how to show P is not equal to NP. This is more dedicated. Okay, what is known to the probabilistically? The following result is known. So almost all monotone CNFs are dualizable in polynomial delay. So most of the instances can be dualized in polynomial delay. So what they really show is the following. So let's M of n denote the class of monotone CNF of n variable. And M for n denotes the class of 4 tight CNF of n variable. So just forget the 4 tight. This is not important. So, and okay, 2 things. I don't remember, but with Toshiba, we show k tight. If the k is constant, k tight CNF can be dualized in polynomial delay, right? So this is a good class of the function. And if you consider the ratio of these 2 numbers, the size of the m for n divided by size of the m of n. So if n go to the infinity, this ratio go to 1. So it means that almost all function is dualizable in polynomial delay, right? Of course, this is a probabilistic argument. I think 2 researches going on. We don't know how to solve the monotone duality. We restrict the important subclasses to show this is polynomial solvable. This is one research. The other one is how do we generalize this quasi-polynomial result, right? Okay. The first one, for the first one, okay, let's consider the k closed CNF. It's a very simple. I mean the number of the clauses bounded by k. So here we have a CNF. We have a 1, 2, 3 clauses. These are 3 clause CNF, right? And the other one is a KCNF. So each clause contains at most k literals. So again, same instance. So here, this clause, length of this clause is 2. It contains 2 variables. This is 1. This is 2. So it means that this is a 2 CNF, right? The other one is how do I say occurrence, read k CNF. So each variable appears at most k times. So again, this case, so x1 appear twice, x2 appear once, x3 appear once, x4 appear once. So So take a max. This is 2. So this is a lead twice, lead to CNF. These are quite natural classes. Okay. Okay, what is known? Okay, let's consider the K cross CNF. So if K is constant, I don't, okay. If the K is cross CNF, then it is trivial, right? So just expanding formula. Then we have a n to the k terms. Then we delete, I mean, the redundant one. So this is the input polynomial time. The non-trivial case is if k is log. So in this case, expanded DNF has a n to the log n terms, which is not polynomial. But we can do this in incremental polynomial time. I don't want to go to the detail, but I just explain what is known. Okay, these are the ones that KCNF, right? Again, each clause contains at most k literal, right? So if you consider 2CNF, right, then you can see this is equivalent to the, we have a graph, how to generate the maximal clicks, right? This is equivalent to the 2CNF case. So maximal clicks are well-studied topics in the data mining. And currently best one is ours with UNOs. It can be, is a polynomial delay. Delay is bounded by the matrix multiplication. N to the 2.376. It was improved, I mean. Matrix multiplication is improved by recently, but something like this. Okay. And k is constant. Yeah, there's a result we can show. It is incremental polynomial time. But we don't know this is a polynomial delay or not. And if k is log, we don't know. I mean, in the sense of the FPT framework, we don't know this is solvable. I mean, in the FPT. Okay. For the lead case, again, if the k is constant, we can do in the polynomial delay by the Domingo, Misha, Pitts in 1990. And the k is log, then we can show this is an incremental polynomial time. But we don't know this is polynomial delay or not. Okay. Okay. So, okay. This is how they say 3 basic restriction. Number of the clause or number of the occurrence or number of the, how they say, literal which contains that clause, right? Okay, let's consider the other simple decomposition scheme. Okay. Or maybe tired, right? So yeah. Any questions? Yeah. I think that 1 hour talk is enough, but because everybody gets tired, that's which I know. But no questions? Okay. Let's go. The simple scheme, I mean, simple computation scheme for the monotone dualization is the following. Let's phi sub I denote CNF having the first I clauses in phi. So in this case, phi 1 consists of the first clause, just this one. Phi 2 consists of the first 2 clauses, C1, C2, here, and so on. Then let's psi I denote the prime DNF, which is equivalent to the phi I. Then our objective is to compute the psi m. So m is the number of the clauses, right? Then just do this way. For psi 1 is clearly equal to the phi 1. Psi 1 is equal to the phi 1. And to compute psi I, we use a psi I minus 1. So we consider the conjunction of the psi I minus 1 and Ci. and continue. Okay, look at this example. Okay, in this example, psi 1 is exactly equal to the phi 1. This is a, you can see this is a DNF or a CNF, right? Both you can see. This is a psi 1. The psi 2 is so this is phi 1 and phi 2. This, in this case, C1 and C2. So we just expanded the formulas and we get this.
X1, X2 also should be present, I think.
I want to say this is a, you can see this is a one clause. In this case, it's a CNF. If you regard this is a term, two terms, then we can see the DNF. So just a single clause is a DNF and CNF, both. So in this sense, this is the same. The psi 2 is just a compute this a simple way. But you can see to compute psi 3, I mean, you want to dualize the first three clauses. Then use you already know this one is this, right? Use this information and consider conjunction this and this. This is the simplest way, right? We partially already computed and conjunct x1 or x3. Then you get this, right? And so on, right? It looks efficient, right? It looks efficient way, right? Maybe to compute psi 4, we use a psi 3 information, this information, right? But unfortunately, this procedure is not efficient. Look at this example, simple example. We have again, we have a 2n variable, x1 to xn and y1 to yn. Oh, sorry. Sorry. Yeah, and each term is each clause is it looks a complete bipartite graph. Clause consists of some xi to yj. Right? Consider this CNF. So what is a DNF correspond to the phi? This is just two terms, x1 to xn and y1 to yn. Just two terms, right? Yeah, just consider the how do I say expanded case, right? So only two terms, but if you consider these clause ordering, the first clause is x1, y1. The second clause is x2 or y2, and the nth clause is xn or yn. Then, you know, this is 2 to the n terms, right? So output side is just 2, but the intermediate side is 2 to the n. This is bad, right? So we have to take a good ordering. And unfortunately, Takata show, there's no such ordering exists. For any closed ordering, this becomes a super polynomial, right? But the following ordering is good in some case. Okay, this one. This is not closed ordering, so let's consider the phi I, which is a CNF. So C is contains the original CNF phi, and C is a subset, or C uses the first I variables, right? So 0 or 1 is 0. So in this case, there's no clause which use x1 only, right? So here psi 2 is this, because this is only the clause which use only x1 and x2. The other one is x3 or x4 or something, right? And the phi 3 is this. You know, these two clauses, because the other one use x4. right? And then phi 4 becomes now phi. And similar algorithm. We just decompose the original CNF, and we suppose we already compute psi I minus 1. Psi I is a prime DNF, which is equivalent to the phi I, right? Then using the previous information, if you know the psi I minus 1, we use this to compute psi I. Consider the conjunction of psi I minus 1 and delta I. Delta I is a difference of the psi I minus 1 and psi I. Sorry, phi I minus phi I minus 1. Yes. And okay. Good part is this. We have a lot of intermediate DNA, psi I, but all psi, the size of the psi is bounded by the output goal DNA, psi. So this is different from the previous one. And this decomposition schema is considered by Laura and Lenz and Linacam in 1980s, and we modify this scheme and use some other technique, which is used in the 2CNF case. Then we get how do I say, unified algorithms. I mean, essentially we use this, essentially we use this decomposition scheme, but to compute this part, we use Johnson-Yanakakis probability idea. Then we get lead K-CNF and K-CNF case and several other classes, but I don't want to mention this. So this is an efficient and widely applicable result. Okay. Okay, maybe I'll finish the first case, and maybe I explain the part of this generalization of the quasi-polynomial-time algorithm. Okay. Okay, look at the monotone dualization. So this is another view. We have a 0-1 matrix. Here A is a 0-1 matrix. We want to compute a Hilbert basis for the ideal for this polytope. In other words, we want to generate all minimal integral solution of this system. This is equivalent to the monotone dualization. Okay, we have a 0-1 matrix, which is at least 1-1-1 matrix, and X is non-zero. We want to generate all minimal integral solutions. So if we have this CNF, we get this system. A is this matrix. Why this? Because to get DNF terms, right? We consider the expanded case, expanded formula, right? You expand the formula, right? In this case, at least x1 or x2 should be contained, right? Here x1 is contained, it's x2 is contained, right? So it means that this first inequality must be satisfied. X1 plus x2 is at least 1. At least one of them is 1. And similarly, second clause corresponds to second inequalities. X2 plus x3 is at least 1. Right? So on. So it means that each row corresponds to the clause. Right? Okay. Okay. Okay, we have a linear system. So this is a minimal, I want to say this is a minimal solution, right? So in this case, we have a hypercube, and x1, x3 means 1, 0, 1, 0, right? x1 is 1, x3 is 1. Other part is 0. So 1, 0, 1, 0 correspond to the 1, 3, the minimal point, minimal integral point. So x2 and x3, this one is correspond to 0, 1, 1, 0. And x2, x4 corresponds to 0, 1, 0, 1. We have a linear inequality, and we want to compute a minimal feasible solution. Oh, sorry. And each, yes, row, each inequality corresponds to the maximal infeasible point. For example, first inequality, x1 plus x2 is at least 1. Consider maximal infeasible point. Maximal point which doesn't satisfy the first inequality. It means the third one and the fourth one are both ones. And the first two, variables are 0. 0, 1, 1 correspond to the first inequality. So it means the maximal infeasible point is 0, 1, 1. And second inequality corresponds to the maximal infeasible point is 1, 0, 0, 1, complement of the row. The third one is a complement. 1, 1, 0, 0 is a complement. So in other words, a monotone dualization problem is we have this picture, right? We given a top peak of the mountain. How do you compute the bottom of the valley? So if you consider decision problem, we have peaks, 2 peaks. How do you check? This covers the whole space. And we can generalize this way. So the original one is A is a 0, 1 matrix. But we don't care. This is just a monotone matrix. We have a non-negative matrix A here. B is not necessary to the 1, maybe some numbers. And x is non-negative. And x might be bounded. Maybe not bounded. In this case, x plus infinity or bounded, some numbers. We can generalize this, right? And we show, essentially, which Andrew Borosh, Khaled Elbasani and Vladimir Gurevich and Leo Khachiyan, and I show this, general version of the problem. All minimal integral solution of a monotone linear system can be, this is a negative result, cannot be generated. Something wrong, sorry. Can be. Sorry, this is positive result. We can say, we can compute in incremental quasi-polynomial time, right? So this was essentially conjectured oppositely by Laura and Lenz and Nino Kahn in 1980s, but we show positively. We can show, we can generate efficiently. But if you consider the maximal infeasible solutions, then the result is negative. We cannot generate in output polynomial time unless P equals NP. So minimal feasible solution is possible in polynomial time. In quasi-polynomial time, but maximal infeasible one is impossible. So this is a not symmetric result. So this shows how do I say this generalization is not, how do I say, trivial, right? Okay. Okay. Of course, we can generalize more this way. I mean, linearity is not necessary. Important is a monotone property is a separable property. We have a M inequalities. So J is a, right? And Fij is a one variable function, which is monotone. Of course, polynomially computable. Monotone means Fijx is at least Fijy if x is at least y. So essentially, we have a monotone separable function inequalities. Then we get a positive result. So all minimal integral solution can be generated in incremental quasi-polynomial time. Okay. Okay, maybe two other examples, then I finish. Okay. So yeah, consider the efficient point in the discrete probabilistic distribution, which is important to the stochastic programming. Yeah. So here, Xi denotes a random variable with finite support, S. S is a subset of Zn. And the support means only the, yeah, Q in S has a positive probability, and if we sum up, this becomes 1. Okay, sorry, some Japanese. So the point is called P. Okay, given a P, P is a integer. P is a number between 0 and 1. The point X is called P efficient, which is a minimal point such that probability Xi is less than or equal to X is at least bigger than P. This is called P efficient. So for example, we have this is a two-dimensional case. So this point is S, right? This point is probability 0.2, this point is 0.1, and so on. And suppose P is 0.45, then this point is a P efficient. Okay, then we divide it. So the Xi, which is at most X. So look at the left bottom area here. If we sum up the probability, 0.2 plus 0.1 plus 0.1, which is greater than 0.45. So minimal means if you, how do I say, go this way, then it's no longer satisfy this condition. Right? If you go this way, then it becomes, yeah. This is called P efficient. And P inefficient is opposite. The maximal point which satisfies opposite condition. Probability that Xi is at most. So yeah, same. But at most X is at most P. Okay. So this is has an application to the stochastic programming. And one side is positive, the other side is impossible. Yeah, negative. So all inefficient points can be generated in incremental quasi-polynomial time. But the other part, all efficient point is impossible unless P equals NP. Yeah. Okay. Okay. Maybe last one. Okay. So consider maximal K box, hyperrectangle. So we have a point. Set S denotes a set of points in Rn. So here two-dimensional case. And sorry, this is an integer, K, which is at most size of S. Then K box is a hyperrectangle box whose interior contains at most K point. So in this example, right, this rectangle, the interior contains 3 points, right? And consider the maximal such one. So this is a maximal, right? If you enlarge, then it contains sorry, at most. In this case, it contains 4, right? If you enlarge, right? And maybe we can generalize this way. So, but I want to, skip this. So, this box problem has an application to the machine learning and the computational geometry and data mining. We show that all maximal K boxes can be generated in incremental quasi-polynomial time. Yeah. Okay. How much time? Maybe I skip my.
When were you first doing this?
Yeah, but this is a technical detail. So, okay.
Maybe this is an exercise.
Yeah. All right. Okay, I want to say that first, that this generation problem is considered in this area, but nobody can get a positive or negative result. We get a positive result, partially positive result, I mean the quasi-polynomial result, because we show this is, how they say, at least as hard as monotone dualization first, right? And we, how they say, extend our idea to this problem. That's why nobody show this can be solved in quasi-polynomial time. For example, this K-box problem and the inefficient point in the stochastic programming. So how to show this? We reduce, for example, maximal K-box problem to the generation problem, of the generation problem of minimal feasible point in some good monotone system in good partial order set. This is the idea. So the monotone dualization case is quite easy, right? It's just a monotone system, and this is a Boolean cube. But good means, for example, this is a good one. That's trivial one. But we have to transform the, for example, K-box problem to this one. This is the first step. And we generate both minimal feasible point and maximal infeasible point. If the poset is good, we can do this. So this is how they say we extend Fredman and Khachiyan's idea to this partial order set, like this. If the partial order set has a good property, we can generalize this. This is the first part. The other one is, how do I say? Yeah, okay. But we know that we can generate both minimal feasible point and maximal infeasible point. But we need only minimal feasible point. We don't need a maximal infeasible point. So in general, oops. Oh, something happened. Okay. Yeah. Okay. So we need only minimal feasible point. We don't need a maximal infeasible point. So in general, right, number of the maximal infeasible point is larger than the minimal feasible point. But if we show the monotone system is good, then we can show some good property like this. So for example, maybe I skip the second condition. I just want to explain the first one, dual boundedness. The unnecessary one, the maximal number of the maximal infeasible point is bounded by the quasi-polynomial in the input and the number of the minimal feasible point. If you can show dual boundedness, then the idea works. I mean, dual boundedness implies the output quasi-polynomial time. And maybe skip. So this is some technical issue. Yeah. Yeah. Okay, maybe I just conclude my talk. So I just defined the monotone generalization, definition and application. I hope at least everybody understands this part and some complexity issue. This is enough. These are, how to say, some difficult problems. And I just explained the result here, right? So I don't explain the proof or something. So I hope everybody understands the definition and the current status. So that is enough for me. Yeah. Thank you. Yeah.
Maybe a
Yeah.
simple question for you. As you touched the problem of generating maximal clicks, and this is important for mining communities.
Communities, yes, yes.
In this audience, there are many people interested in data mining. So can you please explain the reduction to dualization problem?
Okay. Okay, first you forget singleton.
You forget it, yeah.
Because any, how do I say, term contain x4, for example. So then we just ignore this. So then we have then every clause become quadratic. Every clause contain exactly two variable, right? Then we have to take a complement or not.
Yeah, you interpret them as edges.
Yeah. Just okay.
How you encode the clicks.
Okay, okay, I see. We have to, how do I say, consider complement of the graph. If you consider this way, this corresponds to generating all minimal covers, vertex cover, minimal vertex cover. Take the complement, it is corresponds to maximal independent set. So in this sense, we have to consider the complement of the graph. So in this case, we consider the graph which doesn't contain the h, x1, x2, which does contain x3 and x1. Consider this graph. Then computing a dualization problem is a maximum click problems.
Yeah, but as input you have cover, or you have covers, or you have.
Yeah, but okay, the simplest way is that if you construct a graph such that there is a h, x1 and x2, and x3 and x1. If you consider this graph, the dualization problem corresponds to the minimal vertex cover generation, right? Right. So it means that we have to consider the complement of the graph. So in this sense, here we draw the h, which is not this one, not this one. So we have a graph which contains 2, 3, for example, 2, 3, yeah. Then it becomes correspond to the maximal click. You understand, right? Yeah. Yeah, maybe if you have a whiteboard, maybe easier. Yeah. 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 Yeah.
No more questions, and maybe a remark that another important connection to data mining. Just how to say, just a hint how it's related to data mining. You can see your binary data table as a DNF in conjunction of binary attributes which are in the description of particular object. And then you take disjunction over all objects, and in this way you encode your data. You encode your data by a DNF.
Yes.
And data mining often is understood as getting rules from your data. implications. And these are encoded naturally as CNFs.
I see, I see, I see.
So then coming from data to rules to implication set is converting DNF to CNF.
Yeah, yeah,
This
yeah.
way,
Yeah, yeah.
roughly.
Yeah, roughly, I
You get
yes,
the
yes.
idea of
Yes, yes.
what count is related to data mining.
Okay, okay, I want several ways, for example. For example, you know that, how do you find a maximal frequency set or something? Minimal frequency set, which the maximal frequency set, or I forgot.
Maximal frequency sets
Right.
are important in practice.
Right. Yes, yeah. Of course, this can be regarded as a monotone system of the simple, right? Poset, right? So we can show, essentially, I show finding a maximal frequency set is NP-hard. But using, how do I say, our technique, we show the minimal infrequency set is possible in quasi-polynomial time. Yeah, but this is how to say one way. But how do I say? Yeah, for example, the box problem. It's also related to the data mining.
Yeah, just for the students, maximal frequent item sets are important for. From them, you directly obtain association rules, so probabilistic rules, saying that if A, then B with probability higher than.
Yeah, but if you consider probability, then it doesn't become the monotone system. Just consider frequent. Yeah, then it becomes a monotone system. But unfortunately, this is a NP-hard. Yeah.
Thank you.
Thank you.